Imagine for a second, right, that you've got a blank check.
A literal blank check.
Yeah, a blank check. You have the world's best engineers, you have unlimited electricity, and your one goal is to build the smartest entity on the planet.
Naturally, your first instinct is probably to just go big.
Exactly. You assume that if a human brain is smart, then a digital brain 10 times the size must be a genius.
Right. The bigger is better hypothesis. I mean, it's been the driving force of the entire AI industry for the last decade, essentially.
More compute, more data.
More parameters.
Yeah, and that equals more intelligence. Or at least, that's the hope.
But the real question is, does it actually work like that?
Exactly. And that is what we are asking today. If you build a digital brain with hundreds of billions of neurons and you feed it the entire internet, do you get a super intelligence?
Or do you just get, clumsy giant? Something that knows a lot of trivia but can't really reason its way out of a paper bag.
Right. And to answer that for you today, we are going to unpack a massive technical paper from DeepMind.
Yes. It's titled Scaling Language Models: Methods, Analysis, and Insights from Training Gopher.
Gopher, which is a fitting name for something that digs deep. But physically, or I guess digitally speaking, this thing is a giant.
Oh, absolutely.
We're talking about a 280 billion parameter language model.
Just to set the stage for everyone listening, because we do throw these numbers around a lot in this space.
Well, what does that actually mean?
When we say parameters, what are we actually counting? Well, think of parameters as the synapses in a brain.
Okay.
They're the adjustable weights, the connections that the model uses to actually process and store information.
So the connections between the digital neurons.
Exactly. And the more parameters you have, theoretically, the more nuance, the more facts and patterns the model can hold on to.
Right. And for context, GPT-3, which obviously made huge waves when it came out.
That was about 175 billion parameters.
And Gopher is 280 billion.
It is significantly larger.
So the mission for this deep dive is clear. We aren't just here to marvel at the sheer scale of this thing.
No, we really need to understand the implications of that size. DeepMind didn't just build Gopher and call it a day.
Right. They ran it through an absolute gauntlet, something like 152 different tasks to see what broke and what worked.
Which lets us look closely at these scaling laws, like what superpowers actually unlock when you hit 280 billion parameters.
And maybe even more interestingly, what stays stubbornly stupid no matter how big you build it.
That is the fascinating part.
Plus, we are going to look at the behavior of the model. We'll talk about toxicity, bias, and the problem of a machine that sounds incredibly confident even when it's completely wrong.
The hallucination problem.
Yes.
It's a big one.
Yeah.
And the findings in this DeepMind paper by Ray Borgo and the rest of the team are incredibly revealing.
But let's start at the beginning. If you are raising a giant, you have to feed it.
You do.
So what exactly is the diet of a 280 billion parameter model?
Well, you feed it massive text.
Massive text.
That is literally the name DeepMind gave the data set. It comprises roughly 10.5 terabytes of text.
10.5 terabytes.
Yeah.
Just to put that in perspective for you, if you tried to read that much text, and let's say you read a full book every single day,
It would take you tens of thousands of years.
it's just an incomprehensible amount of reading.
It is. But it's not just about the volume here. This is where the paper gets really interesting from a data science perspective.
How so?
Well, in the past, researchers would often just scrape the raw internet. Reddit, random blogs, Twitter.
Just dump it all into the neural network.
Right. But DeepMind was much, much more curated with Gopher.
Yeah, I was looking at the breakdown in the paper, and the ingredients of this dataset seemed very intentional. It wasn't just a random buffet.
No, it was a very balanced diet. They used a specific mix.
Okay, what was in it?
So they had Massive Web, which is their filtered web text. They had C4, which is another massive web scrape.
Right.
News articles, GitHub for Code, and Wikipedia. But the ingredient that really stood out to me, and what distinguishes Gopher from a lot of its predecessors, was the books.
Yes, the books. I saw that. They heavily emphasize books compared to earlier models.
Precisely. In Gopher's training mix, books made up a sampling proportion of roughly 27%.
And what was it for GPT-3?
In GPT-3, books were closer to 16%.
So a pretty significant jump. Why does that shift matter, though? I mean, is a model trained on books inherently smarter than a model trained on web articles?
It's about the structure of the data itself. Think about web text. It's often short, it's chaotic, disjointed.
Like a comment section.
Exactly. A comment section is just a series of disconnected yelling matches. A tweet is short. But a book A book is 80,000 words of coherent, long-form narrative,
Right, it takes you on a journey.
and it requires the model to track ideas over long distances. To understand character arcs or follow a really complex logical argument from chapter 1 all the way to chapter 10.
That makes total sense. If you want a model that can actually reason and hold a train of thought, you have to feed it data that possesses a train of thought.
Exactly. It's the difference between snacking on candy and eating a really complex, nutritious meal.
But there was another detail in that diet section that I found crucial for anyone interested in how these AI systems are built.
The filtering.
The quality control pipeline. Yeah, they didn't just scrape the text, they really scrubbed it.
This is the quality over quantity argument in practice. They implemented this massive pipeline to filter out non-English text, sure, but the big one was removing repetitious text.
Repetitious text, like a copy-pasted spam.
Spam, yes, or just the weird glitches you find on the web where a single phrase is repeated 50 times.
Oh, like a broken web page?
Right, or the exact same boilerplate copyright notice appearing on a million different pages. It turns out if you train a language model on repeated phrases, the model develops really bad habits. It starts to get stuck in loops when it generates text. It's almost like a song getting stuck in your head. It just outputs the same sentence over and over.
So if the training data stutters, the AI stutters.
Basically, yeah. DeepMind found that simply filtering for high-quality, unique text dramatically improved the model's performance downstream.
It's the old garbage in, garbage out rule.
But applied at a petabyte scale. They prove that a smaller, cleaner data set is often way better than a larger, dirtier one.
Okay, so they've built this massive brain. They fed it a high-protein diet of books and perfectly clean web text. They trained it on 300 billion tokens.
Yep.
Now comes the moment of truth. The report card.
The results.
Did the extra 100 billion parameters actually make a difference?
So short answer is absolutely. But, as always, with a lot of nuance.
Right.
Gopher outperformed the state-of-the-art models at the time, things like GPT-3 and Jurassic 1, on roughly 81% of the comparable tasks.
81% is a massive blowout.
Yeah.
I mean, that justifies the electricity bill right there.
It really does.
But let's unpack where it actually won, because that tells us a lot about what scaling up a computer actually achieves.
The biggest leap was in what researchers call knowledge-intensive tasks.
Like trivia.
Trivia, general knowledge, fact-checking, and reading comprehension. It turns out that scale acts kind of like a knowledge sponge.
A knowledge sponge.
Yeah, the bigger the model, the more raw facts it can soak up from its training data, store in those parameters, and then recall later.
There was one specific benchmark in the paper that really jumped out at me, the RACE-E test. Can you explain what that is for the listener?
RACE-ES is a reading comprehension test that was originally designed for Chinese high school students learning English. You read a passage, maybe a story or a news article, and then you answer complex multiple-choice questions about it.
So it's not just, find the specific word in the text.
No, it's testing true comprehension. You have to understand the meaning, the implied context.
And how did Gopher do?
It crushed it. Previous state-of-the-art models were scoring around 47.9%.
So they were failing the class, essentially.
Pretty much. But Gopher jumped to 71.6%.
Wow, that is a massive delta. Going from 47 to 71 is the difference between an F and a solid C-.
Or maybe a B-, depending on how you curve it.
Fair enough.
But importantly, it puts it within striking distance of human performance, which on this test is estimated to be around 94%.
So Gopher isn't perfect, but it moved the needle from confused student to competent reader.
Just by adding scale.
It also dominated the MMLU benchmark, didn't it?
Yes, the massive multitask language understanding test.
Which is like the decathlon of AI testing.
Exactly. MMLU covers 57 different academic subjects. We're talking elementary mathematics, U.S. history, law, medicine, computer science.
Everything.
Everything. And Gopher hit 60% accuracy across the board.
What was the previous best?
Well, it significantly beat GPT-3, which was sitting at roughly 43.9%.
So if I need someone to win a pub trivia night, or summarize a dense medical textbook, or explain an obscure historical event,
Gopher's your guy.
The scaling hypothesis works. Bigger brain equals more knowledge.
Yes. For facts. For information retrieval. For recognizing patterns in language. But.
There's always a but.
And this is the big but of the whole paper. There's a ceiling.
The ceiling. This is the part of the deep dive that really felt like a plot twist to me. Because you'd naturally assume if it gets that much smarter at history and medicine, it should get smarter at everything else too.
Right, a rising tide lifts all boats. But that didn't happen here.
No, it didn't.
And this is probably the most critical insight for anyone trying to understand the actual limits of current AI. While scale unlocked this amazing encyclopedic knowledge, it provided diminishing returns on logical reasoning, common sense, and mathematics.
Mathematics specifically seemed to be a total disaster zone for Gopher.
It was. In tasks like abstract algebra or high school mathematics, Gopher showed little to no improvement over much smaller models.
In some cases, it even performed worse, right?
Just slightly worse on certain splits.
Wait, how could a computer be bad at math? It's a computer. It is literally built on math.
I know, it's the ultimate irony. But you have to remember what Gopher actually is. It is not a calculator.
Right.
It is a transformer model, a text predictor. Its entire job is just to predict the next most likely word in a sequence.
So when it solves a math problem?
It isn't performing a step-by-step calculation in a CPU. It's trying to predict what text usually follows the characters 2 + 2 =.
So it's basically memorizing the look of a math problem rather than understanding the underlying logic of it.
Exactly, and that highlights the massive difference between knowing and reasoning.
Right.
Math requires multi-step, rigorous logic. You can't just recall the answer from a database. You have to derive it from scratch.
So simply making the model bigger helps it memorize more textbook examples of equations.
But it doesn't teach it the logic required to solve a completely novel problem.
It's like a student who memorized the answer key to the practice test, but then completely bombs the final exam because the teacher changed the numbers.
That is a perfect analogy. And it wasn't just math either. Gopher struggled with common sense benchmarks too.
Like Hellaswag.
Hellaswag, yes. And PIQA, which stands for physical interaction question answering.
Give me an example of a PIQA question. What is it actually asking the model to do?
It asks questions about how physical objects interact in the real world. So it might say something like, to separate egg whites from the yolk, you should. And then it gives two options.
Okay.
One is the correct cooking method, using the shell halves. And the other is something absurd, like smash the egg with a hammer.
And Gopher struggles with that.
It doesn't struggle with the super easy ones, but on the complex physical interactions, it trails behind human performance significantly.
Interesting.
It strongly suggests that reading a billion text descriptions of an egg is not the same thing as fundamentally understanding the physics of an egg.
So we have this entity that is a total genius at history and biology, but it fails high school algebra and lacks the common sense to crack an egg properly.
That's the reality of it.
That is such a fascinating lopsided profile.
It tells us that scale isn't a magic wand.
Yeah.
It fixes some things beautifully, but it ignores other deficits entirely.
Now, we need to pivot to a very important section of this source material. We've talked about capability, what it can do, but DeepMind dedicated a huge section of this paper to behavior.
Specifically regarding toxicity and bias.
Right, and rightly so. These models are trained on the open internet, and the internet is, well, it's the internet.
Exactly. It's full of brilliant, diverse opinions, but also a massive amount of hate speech, bias, and toxicity.
So the researchers wanted to know, does making the model bigger make it more or less toxic?
And the answer they found is almost a paradox.
Walk us through it. What did they test?
They used a data set called real toxicity prompts. Basically, you feed the model a slightly toxic or provocative starting sentence, and you see where the model goes with it.
Like, does it de-escalate the situation, or does it double down?
Exactly. And what they found was that larger models, like Gopher, were actually more likely to generate toxic continuations than the smaller models.
Wait, let me get this straight. We spent millions of dollars, used all this electricity to build a bigger brain, and it became more toxic.
If you prompt it with toxicity, yes. And the reason why is fascinating from a technical standpoint. It isn't because the model is inherently evil.
Right.
It's because the larger model is just better.
Better at what? Being a jerk.
Better at following the pattern. Better at understanding context and tone.
Oh, I see.
Think about it. If I start a sentence with a slur or a really angry rant, and I ask the model to complete it, the statistically probable continuation of that text is more anger.
Because it's trying to match the vibe.
Right. A smaller, dumber model might lose the thread of the prompt and just say something random about kittens. But Gopher stays on topic. It mimics the input perfectly.
So because it's a better, more accurate mirror of human language, it's a better mirror of human ugliness when you push it in that direction.
Exactly. It has higher fidelity. But here is the flip side of that paradox.
Okay.
While it generated more toxicity when it was provoked, it was significantly better at classifying toxic text.
Classifying it.
Yeah.
Yeah.
When they tested it on the civil comments dataset, which is a moderation benchmark, they found that the larger Gopher got, the better it was at identifying, hey, this is bad stuff.
That is wild. So it knows the text is toxic. It can look at a sentence and accurately say, that is offensive. But if you ask it to write it, it does it anyway.
Because that is what it thinks you want it to do. It is a completion engine.
Yeah.
It isn't an autonomous agent with a moral compass. It is a statistical prediction machine.
Right.
Unless you explicitly fine-tune it to refuse those prompts, which is a whole separate layer of safety work,
Yeah.
it will just give you exactly what you ask for, amplified.
They also looked at bias and how the model speaks about different demographic groups, right?
Yeah.
What did they find there?
They found really clear evidence of what is called dialect bias. They measured this using something called perplexity.
Perplexity, what does that measure?
It's essentially a metric for how confused or surprised the language model is by a piece of text.
So lower perplexity means the model understands it better, it finds it more predictable.
Exactly. And the model showed much higher perplexity when reading African American English compared to standard white-aligned English.
Which goes right back to the training data we talked about earlier. If the books and the Wikipedia articles it read are overwhelmingly written in standard English, that's what the model learns is normal.
Precisely. It ends up treating African American English almost as an anomaly or an error, simply because it wasn't represented as heavily in that massive pile of text.
And the researchers found gender biases too, didn't they?
They did. Even at 280 billion parameters, Gopher still strongly associates occupations like nurse or receptionist with females and engineer or CEO with males.
Did the scaling help with that at all? Like, did the bigger model get less biased in that regard?
Not consistently, no. The relationship was really messy. It depended heavily on how you actually phrased the question.
Like the prompt template itself.
Right. Changing the prompt from "the nurse was A" to "the nurse is A" could completely shift the bias results.
Wow.
It just shows that these biases are deeply, deeply baked into the statistical patterns of the language itself. Scale doesn't just wash them out. Sometimes it actually crystallizes them.
So we have this massive, highly knowledgeable entity that is slightly mathematically challenged and will happily spew toxicity if you nudge it the wrong way because it's just trying to complete the pattern.
That's the summary.
But what is it actually like to talk to it? Because the paper discusses dialogue specifically.
This was a really interesting experiment they ran. They compared two different versions of the model for conversation.
Okay.
Dialogue prompted Gopher, where they just gave the standard base model a script to act like a chatbot.
Basically just putting in the prompt, you are a helpful assistant, talk to me.
Exactly. And they compared that to dialogue-tuned Gopher, where they actually fine-tuned the weights of the model on real human conversations.
Now, usually fine-tuning is where the magic happens. That's how we get from a raw text predictor to a polished chatbot product. You train it specifically to be a good conversationalist.
You would think so. But the big surprise here was that human writers didn't actually prefer the fine-tuned version over the simple prompted one in any significant way.
Really, all that extra training didn't make it a better conversational partner.
Not significantly, but honestly, the real issue they ran into wasn't the style of the conversation.
What was it?
It was the content. And this brings us right back to the hallucination problem we mentioned earlier.
Ah, yes. I love the examples they provided in the paper here because they are just terrifyingly confident.
There really are. There's this one transcript in the paper where a user is talking to Gopher about cell biology.
Okay.
And Gopher sounds incredibly professional. It's using all the right scientific jargon. It correctly identifies E. coli.
Sounding like a true expert.
Totally. But then it states, with zero hesitation, that only prokaryotes are single-cell organisms.
Which, for anyone who might have forgotten their 10th grade biology,
is completely wrong. Amoebas, yeast, those are eukaryotes, and they are single-celled. But Gopher just stated the falsehood as an absolute, undeniable fact.
But the mass example from the dialogue transcripts was even better, or worse, depending on how you look at it.
Oh, the Euler identity.
Yes. Walk us through that one.
So the user asks Gopher to evaluate a very famous mathematical constant, e to the power of I pi plus 1.
Now, anyone who has taken higher level math knows Euler's identity. The answer is 0. It is widely considered one of the most beautiful equations in all of mathematics.
Right. And what did Gopher say?
Gopher said 2.
2.
And here's the absolute kicker. The user pushed back. They asked the model, are you sure? Do you have any uncertainty about that?
And Gopher replied, no. The answer is 2.
No uncertainty. That is the literal mansplaining of AI.
It really is. And that's exactly the danger with these scaled-up models.
Yeah.
The model mimics the style of an expert perfectly.
The sentence structure, the authoritative tone.
Yes. But it lacks any internal verification mechanism. It doesn't check its work against a database of truth before it speaks. Right. It just predicts the next most likely word.
It's truthiness rather than true. It feels true statistically, so it says it.
Exactly.
Yeah.
And for a user who doesn't actually know the answer beforehand, that confidence is incredibly deceptive. If you ask it about a complex topic you don't know, you have almost no way of knowing if it is hallucinating or not.
So bringing this all together, we have Gopher, 280 billion parameters, a massive, undeniable feat of engineering. What is the final verdict from DeepMind?
The verdict is that scaling absolutely works for becoming an encyclopedia. If you want a system that knows raw facts, excels at reading comprehension, and can parse complex texts like medical journals, bigger is undeniably better.
Wow.
But it hits a very hard wall with logical reasoning and math.
Yeah.
You cannot just scale your way to a reasoning engine.
Right.
And critically, it inherits the biases and the toxicity of the internet it consumes.
And we should briefly mention the physical cost of all this. The paper notes that training this thing required massive compute using TPU-v3 chips. We're talking about huge, huge amounts of electricity.
Right. And the paper actually ends on a very forward-looking note about efficiency.
What do they suggest?
They suggest that just building bigger and bigger dense transformers might not be the sustainable path forward. They point toward architectures that can retrieve information.
Like looking it up in a database on the fly.
Yes, rather than trying to memorize the entire internet within its own parameters.
Because at some point, you can't just keep adding zeros to the parameter count and the electricity bill.
Exactly. We need smarter, more efficient architectures, not just bigger ones.
So here is the thought I want to leave you, the listener, with today. We have built a machine that can classify toxicity better than it can avoid generating it. It can sound exactly like a tenured biology professor while making basic factual errors, and it can read an entire library but can't solve a high school algebra problem.
It really forces you to ask what intelligence really is.
Right. Are we actually building a mind, or have we just built a very, very sophisticated mirror of human knowledge with all of our flaws, contradictions, and biases reflected right back at us?
If you can perfectly recite the textbook, but you can't solve the problem, do you really understand? Or are you just repeating what you've heard?
I think Gopher shows we have completely mastered the repetition part, but we are still searching for the understanding.
Well said.
That is the big question for the next generation of models to answer. Thank you for joining us today and diving deep with us into the mind of Gopher.
It was a pleasure.
We will see you on the next deep dive.